Welcome to the Theta Oilfield Services Rod Pumping Optimization video podcast. This is John Zvinos. The following podcast is a presentation given at the 2009 Southwest Petroleum Short Course in Lubbock, Texas. All right, let's get started. Good morning. My name is John Zvinos with Theta Oilfield Services. And the first presentation that I'm going to be talking to you about is rod pumping educational animations. You know, there's a lot of things you cannot see when you go out to a well. You can see the pumping unit moving up and down, but you don't see the pump. You don't see how the pump works. You don't see the stretch in the rods. You don't see exactly what happens when you have gas interference or fluid pound. So because I teach a lot of these rod pumping optimization courses that a lot of you have been in, I had a need to be able to explain this better rather than trying to describe it with words. So that was why we came up with these animations. And these animations are very hard to come up with. You know, they take a very long time to develop. So they were originally developed, you know, for the purpose of teaching. But of course, a lot of people saw them and they say, well, you know, it would be nice if we had these. Maybe we want to make a presentation and show some of these to our people. So at first we said, well, you know, maybe we'll come up with a screensaver. So we came up with a screensaver and we made that available. But people weren't happy with that. They say, well, you know, that's not quite what we need. So then we came up with actually a program called XANIMATE that plays these animations and also explains what each animation is. And you can also launch each of these animations like through a PowerPoint presentation. So people were satisfied with that. And of course, you know, we also have this built into our Xbox software. Those of you that have Xbox may know where that capability is. So when Xbox says, you know, you have a leaking traveling valve, you can actually play the animation of a leaking traveling valve and see exactly what that is. These animations cover both the pump, how it works, and also the whole system. For example, let's take a look at one of these. This shows how the pump works. I mean, you know, I can spend a lot of time trying to explain how the pump works, or I can show you this and you can see for yourself. You know, as you can see on the upstroke, as soon as the plunger starts to move up, the traveling valve closes, it picks up the load, it carries the load for the rest of the upstroke, and then on the downstroke it releases the load. This is a full pump with no mechanical problems. So it clearly shows you how the pump works, but it also shows some other things that you may not be aware of, and that is like how the fluid level changes. You know, in the upstroke, when the pump starts to take the fluid level in, the fluid level in the wellbore goes down a little bit as more fluid comes in to refill the wellbore on the downstroke.
John, where's the sound? That's part of the fun.
Yeah, you'll see. It's coming up. Or you might want to see how the whole system works. You know, this shows a whole system animation. It shows both the surface and downhole dynamometer card simultaneously, and it shows the whole system. It's kind of loud, so let me lower the volume here. Now, Lynn before was talking about, you know, the stretch of the rods. That when the polish rod moves up, the plunger doesn't move up at the same time. Well, you can see that here. I mean, look at the surface card. You know, when the polish rod starts to move up, the plunger doesn't move up. The rods have to stretch first before the plunger moves up. And actually, in this case here, because we have fiberglass rods with steel on the bottom, the polish rod has to travel all the way up here, like halfway up on the upstroke, before the plunger starts to move up because of the stretch of the rods. And the same thing on the downstroke. You know, the rods have to unstretch before the plunger can move down So the polish rod is like halfway down here on the downstroke before the plunger actually moves down. So, you know, if you're at the well side and you look at the polish rod moving up, you might think the pump is moving up, but that may not be true at all.
What's the little bounce that you're talking about?
Actually, that is not a bounce in position, but rather a bounce in load. Because remember, you know, waves are moving up and down through the rod string, and as these waves reach the pump, they can make the load fluctuate. So you see sometimes a bounce, what it looks like a bounce, like right there, and it's simply a fluctuation in load as the waves hit the pump. And you know, the reason why these animations are so accurate is because we actually use the wave equation to develop the data that went into the animations. The pumping unit kinematic calculations that we have in our software, which are an exact way of modeling the pumping unit, were used to create each frame of these animations. So, we use the actual dimensions of the pumping unit to build the exact frame. So everything is exactly to scale. And also, you know, the location of the top of each of the sections in the rod string was calculated with RodStar, our predictive software, and how it moves. You know, all that information was then used to develop each of the frames in the animation. That's one of the reasons why these take so long to develop and they're so difficult to develop. Yeah. I'm sorry?
Can you speed it up?
Well, this is for a particular condition. You cannot interact with it as it is here because this takes like a whole day to develop, to render. You know, it's sort of like the way they make movies in Hollywood. I mean, you know, it takes a long time to do. So it's not an interactive animation. Okay, let's take a look at some other animations here. You know, in case you were wondering what is the difference between a conventional and a Mark II for a well that has fiberglass and steel rods, this animation shows both at the same time. It shows the Mark II and the conventional side by side with the same well, the same pump size, the same rod string, the same pumping speed. Everything is exactly the same except in one animation, on one side you have the conventional unit and on the other side you have the Mark II. So you can see, it's very interesting to see the difference. You know, you can see the dynamometer card is different. You can see that the polish rod velocity, you know, is different. You know, the Mark II, of course, has a slower polish rod acceleration on the, well, not acceleration, but it has a longer time-wise stroke length, so it has lower acceleration and lower dynamic loads than the conventional. But then on the downstroke, the Mark II has to go faster than the conventional. So those differences show up as differences in the way the rod string moves and the way the stress is propagating the rod string. That explains the differences that you see here. Okay, any questions on this? Okay. You know, we also have animations for like different kinds of pumping units, like the Rotaflex. This is a Rotaflex animation with steel rods. As you can see, the delay between what happens at the surface and what happens at the pump is not as big because even though the steel rods stretch, they don't stretch as much as fiberglass rods. And also notice the movement of the plunger. It's not moving in a smooth manner. Like it moves, it pauses a little bit, or it slows down a little bit, then it moves again. And that has to do with the waves that are moving up and down through the rod string. You know, the Rotaflex pumping unit, when it picks up the load, it puts a big shock loading into the system. And you can see that here, you know, the surface card. When it picks up the load, there is a big increase in load. And that creates a wave that moves up and down through the rod string, and as that wave reaches the plunger, it makes the plunger either slow down or speed up. So that's why you can see that the position, you know, the movement of the plunger is not as smooth as you might think. It kind of speeds up and slows down. This is an interesting animation here. This is actually based on a real well. I remember many years ago I had gotten a call from the field from a guy who had a problem with a well where they thought the pump was bad. They would because the production would go down. The production was supposed to be like 300 barrels a day, and it was almost, like about a little over 100 barrels a day. So they thought the pump was bad. They replaced the pump. They would go back in. At first, the production would go up, and then they would drop again. So they couldn't figure out what was going on. Well, this animation is based on that case. What was happening was that they had the fiberglass, this is a fiberglass and steel design, and the fiberglass rod diameter was too small, resulting in excessive stretch. As a matter of fact, the stretch was so large when the well would pump off or get close to being pumped off that there was so much stretch in the rods that you hardly had any stroke at the pump. I mean, here you basically have to go all the way to the top of the upstroke before the plunger moves up, because basically all you're doing is stretching the rods back and forth. You can see that very clearly here. So this is excessive under travel because of too much stretch in the fiberglass section. Okay, so the solution here was to use larger diameter fiberglass rods, because that still gives you the benefit of using fiberglass and steel, of reduced loads and so forth, but it doesn't have as much stretch in the rods. And I have the after here to show you what happens when you use larger diameter fiberglass rods. You can see that here. Because the rods are bigger, they don't stretch as much, so the plunger starts to move up a lot sooner than before. So we have a longer stroke at the pump as compared to the surface. Yes?
John, is there any correlation of traveling valve velocity versus pump wear? I mean, here we've got a pump traveling valve that's zipping up and zipping down pretty fast.
Well, it's all relative. This is relative to the surface speed, of course. So depending on the pumping speed, there's going to be, I'm sure there's some correlation. I haven't done any studies myself to show that, but it would only make sense that if the plunger is moving faster, there'll be more wear.
Or maybe the other one where that plunger was starting and stopping and starting and stopping.
Mm-hmm. Yeah.
You would think you'd like to have your traveling valve moving nice and easy and
Yeah.
not a lot of starts and stops.
Yeah, but what this reminds me of with your question is, I wanted to bring up the fact that when you have over travel, which in the traditional definition of over travel, you have a longer stroke at the pump than you have at the surface, that actually makes the plunger move faster, because the plunger has to cover the same distance, the longer distance at the same time that the polish rod covers the upstroke and downstroke. So if you have 100 inches at the surface and 140 inches at the pump has to move 140 inches at the same amount of time that it takes to move 100 inches at the surface. So the plunger is moving a lot faster. So if you have like fluid pound, when you have over travel, it's going to be a lot worse than if you have under travel, because the plunger has to move faster. I mean, you can see that here. You can see how fast the plunger is moving here, but if I go back to the previous animation where we had the under travel, you can see that it goes a lot slower, because it only has to cover a small distance. I think it was about 8,000 feet. Yeah. It may have been 8,200 or, it was about 8,000. Okay, so another thing that I want to show you is gas interference. Yesterday we spent a lot of time talking about gas interference, and the presenters here were saying that before the traveling valve can open, you have to compress the gas that's in the pump. And you can see that here. You know, the traveling valve doesn't open when it hits the fluid. It opens when the pressure in the pump is high enough to allow the traveling valve to open. Another good one is fluid pound. You know, of course, when you have fluid pound, you have a system that is designed to make a lot more fluid than there is fluid available. So there is extra capacity that you have that cannot be filled with fluid because there is not enough fluid that the reservoir can provide to fill up the pump. So if your system is designed to make 300 barrels a day and the reservoir can only give you 150 barrels a day, you're going to have half full pump and fluid pound. So this animation here clearly shows that. Therefore, you know, the pump is only partially full. And then, of course, when the plunger comes down, it comes down with considerable, you know, speed, especially when it happens in the middle of the downstroke. You know, fluid pound is worse when it happens in the middle of the downstroke because that's when the plunger is moving the fastest. So that's why about 50% pump fillage is going to give you the worst fluid pound. Fluid pound is not as bad as if when the pump is like 80, 85% full, or if it's 10, 15% full, as far as the damage that it does. But when it's about 50% full, that's when the plunger is moving at its fastest, approximately, and it's going to do the most damage.
Would that be considered a vacuum inside the, because you're not compressing anything when the ball is dropping?
It's not a vacuum. You know, the gas in the pump is the same pressure as the casing pressure. So it's low pressure, but it's not vacuum. You know, like if your casing pressure, let's say it's 50, 60 psi, you're going to have a little bit higher than that in the pump because of the gradient of the gas, but not a lot more. So it's going to be low, but it's not a vacuum. And actually, that's really the biggest difference between fluid pound and gas interference. Is in gas interference you have higher pressure gas, and in fluid pound you have lower pressure gas. Okay, now fluid pound, of course, you know, affects the pump, as you can see in this animation, as we saw in the animation. But it also affects the surface. It actually affects the whole system. And this is an animation that shows fluid pound and how that affects the surface car shape. And in this case, we have a reflection that sometimes we see when there is fluid pound. The compressive wave travels through the rods. And in this case, for example, we have fiberglass and steel rods with single bars on the bottom. So when that compressive wave goes through the single bars and hits the interface between the single bars and the fiberglass rods, because of the large change in diameter and material, a lot of that energy gets bounced off and goes back down. And when it reaches the plunger, it makes the plunger temporarily pause or stop, and then it starts to pick up the fluid load, and then it moves again and releases the fluid load. So you have a spike that shows up. That's the reflection of the single bars. You can see that right there, the plunger kind of pauses temporarily. And as it does that, it starts to pick up the fluid load, and then it moves and releases it. And what's interesting is that, you know, you see this when you do a diagnostic analysis of an actual well, but what's interesting is that you can actually predict this with a predictive program. You know, as a matter of fact, this was done with Rodstar, and it matched an actual case almost exactly. So it's something that's there. And there is another example here of another case with fluid pound that has also that spike, the reflection of a single bar. See how fast that load fell on fluid pound?
So in this case, you can have a lot of vertical gas here to help cushion
Right.
downspout.
Yeah. The load only changes when the plunger hits the fluid. Now, another useful application of these animations is to show, different problems at the pump, like, leaking traveling valve, for example. This animation here shows what happens when you have leaking traveling valve. Of course, when you have leaking traveling valve, you're losing fluid load on the upstroke, and you have fluid leaking back into the pump, which makes the pump barrel pressure higher than it would otherwise be. And since the pressure difference across the plunger is what determines the load on the plunger, when that leakage occurs, the load is not going to be as high as when you have a full pump, and it's not going to build up as fast. It'll pick up more load as the plunger speeds up, and when it reaches the middle of the upstroke, you have the highest speed, and that's where you're going to have the biggest pressure difference. But as the plunger goes past that point and it starts to slow down, then it's going to start losing load here. Of course, on the downstroke, having a worn ball or seat, it doesn't affect the loads because the loads are now on the standing valve. So this only affects the top of the stroke, the top of the pump shape.
John,
Yeah.
your standing valve shouldn't open where it's opening, right?
I'm sorry, it shouldn't open?
It shouldn't open right there.
The traveling valve, you said?
The standing valve. The standing valve doesn't open until you picked up the load.
Well, it opens, yeah, I know. This animation is not exact.
You need to delay that.
Yes. These animations are old. I'm going to show you some new ones that we have under development. There is a standing valve leak, kind of the same thing, only reversed. On the downstroke, the fluid load is being put on the standing valve, but if it's leaking, then the pressure inside the pump barrel doesn't go up as fast as it should. So there's a gradual, reduction in load as compared to a full pump. Another interesting animation is when you deal with shallow high rate wells, we call these group 2 wells with fluid inertia effects. These occur when you have typically less than 4,000 foot deep wells with a larger plunger, like 2 1/4 or larger. The dynamometer card for a full pump is no longer a rectangle. It has typically a hump on it like this because of the fluid inertia effects. And also the reason for that, one of the primary reasons for that is because the rostering doesn't stretch. Well, it stretches a little bit, but not enough to absorb the shock of picking up the fluid load. So, you see a large dynamic load on the plunger that causes the dynamometer card shape to be quite different from a rectangle. And also that wave that we put in, that we create when the plunger starts to move up will move through the fluid, and when it reaches the surface, it'll bounce off and come back down, and it will give us a reflection on the downhole pump card. That's what this is. This is the original hump at the beginning of the upstroke, and this is the reflection of that as that wave moves up and comes back down. Also, in shallow wells, we see more high frequency waves because the rostering has higher natural frequency. If I had that slinky that Andy was playing with yesterday, I could show you that. But it basically has to do with because the rostering is stiffer, so it has higher frequency vibrations. That's very typical for shallow wells. Now we saw how the surface surface and down, the whole system works. But let me further explain this wave that I talked about with this animation. This is a group 2 well with high fluid inertia effects. And we use a red bar here to simulate the pressure wave that you put into the fluid when the plunger moves on the upstroke. That is the pressure wave that travels through the fluid, hits the surface, it comes back down, and gives you a reflection right there, which causes the load to go back up on the plunger, but not as much as before. Those of you that don't have these types of wells probably have not seen this before, but We have a lot of shallow high rate wells outside of Bakersfield that do this exact thing, and other parts of the country as well. Okay, we also can simulate, pumping units, just the pumping unit itself, with the animation, and we can better understand how it works. There is the Mark II. You can see the longer, slower upstroke, and then the faster, shorter downstroke. But it's better to compare pumping units on the same slide, like we can do here. This shows a conventional unit, which is the one that has the orange head, of course, and the Mark II in the front. Both are going at the same speed, and they both have the same stroke length. But you can see that the Mark II has a slower upstroke and it's longer as compared to the conventional. But then on the downstroke, the Mark II is faster because it has to make up the lost time, so as compared to the conventional. Yeah.
Is there also a pause at the very bottom of with the Mark II? It looks like on the animation.
What do you mean?
A pause, like right there.
Well, every unit has a little bit of a pause because it has to revert from upstroke to downstroke. It has to go through zero speed. So yeah, and they all have that. The Mark II may be a little bit longer pause. This animation here is for a reverse mark. You can see the crank offset angle here. There are holes on the crank that are at an angle, and also the gearbox is further back as compared to a conventional. This is an air balance unit. I guess for these animations, we might as well go out in the field and take video, right? Those are not as big of a deal as the ones downhole. This is an interesting one. This is a three-dimensional downhole pump animation. Here are the perforations. Gas coming out of solution in the upstroke. The fluid level here, moves down on the upstroke as fluid is entering the pump, and then it goes back to normal on the downstroke as the fluid continues to come out of the perforations. Now, these are the old animations that we had developed, and these are the ones that we have available in this XANIMATE program. But we are working on new ones. And we have a new technology now that we can use to come up with even better animations. And we use flash. You've heard of flash. These are high resolution and scalable animations. What's neat about these new ones is you can zoom in. Like if you want to look at a little part of the animation, a little detail like what happens around the traveling valve, you can zoom in and look at that. Let me demonstrate. Well, these are, we have surface and downhole animations. This is let me show you a surface one. So this is a conventional unit. I can maximize the screen size. I don't lose any resolution. I can zoom in and look at some part of it. See, I can go to view, zoom in. I can zoom in even more. I can move it around as it's zoomed, and I can see different parts of it. Without it losing any resolution. There's the Mark II. See, it's a lot smoother, a lot more realistic. This is a comparison between a conventional and a Mark II. Again, this is with the new style. See, another nice thing about this is you can use different players that are available. And for example, this player right here, I can actually pause this and I can control, well, maybe not this one. It depends how they're built, but you can actually control the animation by moving a slider. I think I can do that with this one. No, maybe not this one. Anyway, we can do this. This is a reverse mark versus a conventional. Now you can clearly see the differences here between the reverse mark and the conventional. The conventional is the one in the back with the orange horse head, and the reverse mark is the one in the foreground with a green horse head. You can see, the pitman arm angle. This is the reverse mark. You can see how that gearbox is further back as compared to the conventional. And you can also see the speed that the reverse mark has a slower speed on the upstroke as compared to the conventional, and then a faster downstroke. See, I can actually use this slider to go back. I can go to any part of the animation here, pause it, go back, look at it in more detail. So it allows me to do some things that we couldn't do before. This is more interactive than the previous generation of animations. This is an animation of a deviated well bore. Again, you can zoom in and look at the rod guides. Or you can look at the surface unit. But what I like the best is the downhole animations. This is a full pump. Again, if I want to look at part of the animation, let's say I want to look at what happens to the standing valve. So I can zoom in, and I can actually go to the part that I want to see and zoom even more. You can see the gas coming out of the perforations. I can look at the traveling valve and how that works.
Are the gas bubbles getting larger?
Yeah, which is what actually happens, right?
Because they collect, they merge together?
No, as the pressure goes down, they get bigger. Here is fluid pound again, but this is better than before, more realistic. See, the gas that goes through is low pressure gas that comes from the casing. So it's slightly higher pressure than the casing pressure gauge shows. So the plunger basically has to hit the fluid to show to unseat the traveling valve. When that happens, especially when it happens in the middle of the stroke, that will give you a large impact, which can cause the rods to buckle, and it puts a big pressure wave in the pump barrel, which can cause a barrel split, or it makes the traveling valve jump off its seat and it can hit the cage and get pitted and so forth. Gas interference is a good one. When you have a gas interference, you have a lot of gas that goes through the pump, and then you have to compress that gas before the traveling valve can open. And when you compress it, the gas will go through, and then it'll hit the fluid, and the fluid will go through. It's actually very close to what you were showing, or what you videoed, right? Yeah, it's pretty close to an actual video of what happens when you have gas interference. You know, the beginning of the upstroke, you're expanding the gas over here. You know, this is the gas expansion part. Both valves are still closed. And then finally, when you expand the gas enough to open the traveling valve and pick up the fluid load, then you have a constant load for the rest of the upstroke. And then on the downstroke, you have to compress the gas in the pump before the traveling valve can open. When you have pump heating down, this is for a tubing pump. You know, you see a spike at the end of the downstroke, right? So here you can see why that is. And again, we can actually zoom in and look at that when it happens. See, some people do this on purpose to jar the valve open when you have gas, right? I mean, you can see that here. If you have unanchored tubing, the tubing is going to move. And this animation shows that. So in the upstroke, as you pick up the fluid load, you're taking the load off the tubing is going to move up. On the downstroke, you're putting load back on the tubing, so the tubing will stretch. And that's why you have the slants on the cars show gradual increase of load on the left side and gradual decrease of load on the right side. Here is the leaking standing valve. So again, what happens here on the downstroke is that you're losing fluid through the standing valve. And again, here I can zoom in and look at that.
Balls out around.
Yeah. You see the fluid leaking out of the standing valve. And the same thing when you have a leaking traveling valve. See on the upstroke, fluid is leaking out. Okay, if you have a bent or sticking barrel, you're going to see a car that looks like this, because when you go past the bent or sticking section of the pump, the plunger has a hard time squeezing through. So the load will go up on the upstroke, and then at the same spot in the pump barrel, on the downstroke, the load will go down. So, and that's exactly the sound you're going to hear when that happens. If you were to go down there.
What example is that?
This is a sticking pump, bend or sticking pump. And actually, if you zoom in here, you can see that the plunger is being squeezed to the side as it goes through that narrow section. You see that? Yeah. This is what happens when you have a worn or split barrel. You know, this is the worn spot in the barrel. When the plunger gets into that section, on the upstroke, it loses its pressure difference and temporarily, a little bit of it, and you're going to see a drop in load as it goes through that section. And then as it goes past that section and reestablishes its pressure difference, then the load goes back to normal. One of my favorites, and I think Andy Cordova would like this one, this is an animation for how a rod pump controller works. This actually shows the whole cycle. You know, at first you have a full pump because there is enough fluid to fill up the pump barrel. But if you continue to pump at a higher rate than there is fluid available, you're going to pump the well off, and when you do that, you're going to have fluid pump, and you're going to actually see that happen. So every stroke, the fluid level goes down. See right here, we're almost out of fluid there. We're a little bit out of fluid. So we have a slight amount of fluid pound. Now we have more fluid pound. The pump is less full than before. And the same thing happens here. Now the pump of controller is going to shut the unit down, or the rod pump controller, I should say. And now what happens in the downtime? Fluid level continues to come out of the purse, right? So it builds over the pump until the downtime expires. And then when the downtime is over, you know, whether it's 5 minutes, 10 minutes, whatever you set your controller for the downtime to be, it'll kick back on, and then now you have enough fluid to keep the pump full. So now the pump starts back up. Now there is enough fluid to keep the pump full for a few strokes, and that cycle will repeat.
That's impressive, John, I like that.
Thank you. And let me show you, this is not finished yet. We're still working on this, but this is a poor boy gas anchor and how it works. Let's take a look at that. See, there's your dip tube, and there is the perforations here. You know, I don't know why this is so dark. It's not that dark on the screen. Maybe this is a high contrast projector or something, but it's not that high on the screen here. You can more easily see what's going on. But the liquid, you know, goes in while the gas escapes and goes up the casing. Liquid goes down and into the pump on the upstroke. So there you can see that. Liquid goes in and in the pump. Yeah, I can zoom in. See the fluid going in and the gas going by? So this is your mat anchor. This is the bull plug at the end of the mat anchor. There's the perfs at the top of the mat anchor. So the liquid goes in, down, and into the dip tube while the gas is produced up the casing. You know, the key to this design, of course, is to have the speed of the fluid be about 0.5 foot per second or less to give the gas a chance to escape. If the speed is higher than that, then some of the gas can be trapped and brought in anyway. I can zoom in even more here. This is the dip tube. Dip, D-I-P, dip tube. So basically what you're doing here is you're forcing the fluid to go down before it can go inside the pump or the dip tube. And by doing that, the gas can escape while the liquid goes in. Okay, so, you know, we think that these animations are very useful because a lot of the things that we can show you cannot see. So it really helps you understand what's happening at the pump and why different things are the way they are. And also, you know, the pumping unit animations, even though you can go take a video of a pumping unit, you can't put two units side by side and take a video. You can't put a conventional and a Mark II side by side going at the same speed. And you know, so, you know, these are still useful in showing the differences for pumping units. And that's it for now. Yes, sir.
Wouldn't it be more useful if this preceded the prior presentation? I mean, it's kind of like, or at least for me, it's the putting the cart before the horse.
I'm not in charge of the presentations. so I can't answer that. Yeah, I mean, these things make it easy to understand what's going on.
Well, I mean, before we get into all the technical data and stuff like that, it seems like this is the illustration that should come first.
Yeah, well, you know, like I said, I'm not in charge of the order of the presentations. But, you know, whether it's before or after, you know, the thing is, by watching these animations, you really understand what's happening.
Yeah, but if you're in a fundamentals
Yeah.
class, where you know as little as I do,
Yeah,
then this leads you a lot more purposefully in a direction of understanding the technical data that is talked about, and this way you relate to it.
sure.
You relate to it in advance.
Well, you know, when they pass out the evaluation form, you can make a note of that. That way they know. All right, any other questions? Okay, let's take a 10-minute break.